Hello everyone, so this is the sixth week of this live tutorial session, and today we'll be discussing some problems related to basis and linear maps. So first, and sometimes we may also go to this um, algebra map. So I'll define those algebra and algebra map first, and linear maps and then we'll go to problem. Okay, so first let me start with VW, the two vector spaces. Uh, so so VW be two vector spaces over a field K, and a linear map between these two vector spaces. So a map A from B to W is linear if it respect the over the same, so it is additive first of all, that f of v1 plus v2 is same as a v1 plus a v2 for all v1 v2 belongs to V, and second one, it is linear with respect to the scalar multiplication also. So if I take C of V, this is same as f of C of LP for C belongs to your field K and V belongs to the vector space V. Okay. If these two happens, then we call a map a linear map. And in some cases we also need this algebra. So and algebra A over a field K is or it has like two structure. As the following structure. So first of all, that this A is a vector space over K, is a vector space over K, and second, in A there is a multiplication defined. So on A there is a multiplication structure. Generally you can say that if you have a ring A and with also a vector space structure, then you say that to be an algebra over this field K. And in A also there is a in this multiplication structure and structure with an identity element. Okay, and algebra map is again that is a linear map, first of all as a vector space, and also it respect the multiplication structure. So an algebra map A from two algebra say over the same field K, AB or algebra over same field K, is a K vector space linear map and it also respect the multiplication structure, and I write f of a1 a2. This is the product in a, that is same as I take the fa1 fa2 and then multiply in b, so it should satisfy this for all a1 a2 belongs to a. Then this is an algebra map. Okay, we may use these two things later on, but let us start with some basic example, basic exercise. Okay, so first one is if you have a non-zero element, so r plus cross, this means that it is a fixed positive real number, and this, then you take any a belongs to r and phi belongs to r. You can define a map from r to r. Simply that takes t to a sine omega t. Omega is that fixed number, and omega t plus phi, and you define your w to be all such function for varying a and phi. And then you need to show that this w is a r subspace of the r vector space r power r. That means that consists of all real valued function on r, and then you need to find a basis, r basis of this r subspace w. Okay? Once you get the r basis, then you can say dimension of that w. Okay, so to show this w is a r subspace of the r vector space r power r, what you need to check? So you need to check two things, right? So whenever you need to check this w is a subspace of some bigger vector space, so you check that, to check w is a subspace need to check that if I take two elements from this w and add them, that will give me an element in w itself. That means in this particular case, if I take a phi and f b psi, for a b phi psi all belongs to r, then this should belongs to w. And second one is, if I multiply by any element c from r with f phi, that also belongs to w. These two conditions I need to check. So for that, if I need to represent this a phi plus f b psi in the form of some a prime theta or something, so that I can say that this belongs to w. Similarly here, so let's do that first one. Like if I have a phi plus f b psi, this is a function of t. This is by definition that it is a sine omega t plus phi, and second one is just b sine omega t plus psi. So I need to so that this I can write in the form of some a prime sine omega t plus theta or something. Okay, so to do that, first of all we need to change this phi and psi to something similar. So I'll just use it here, that sine omega t plus phi, and this I will change like b sine omega t plus phi plus psi minus phi. Okay, this is still omega t plus psi, and this I can break by like sine sum formula. So that will give me, this is sine omega t cos psi minus phi. So that is, if I take common with this term, then that will give me b cos psi minus phi and with sine omega t plus phi, and the remaining term was the sum. In the sum formula there is another term, this b like b sine psi minus phi cos omega t plus phi, right? So it is just like splitting this sine omega t plus phi, so that is sine omega t plus phi into cos psi minus phi in plus cos omega t plus phi into sine psi minus phi. Okay, now you define this to take some a prime and take this to b prime. Okay, then I want to arrange this in a form of sine omega, like so that I can want to write this as a like some formula for sine, right? So I need to take this a prime by, so let me just, it is the usual thing that you take a prime square plus b prime square. So this is become now a prime by root over of a prime square plus b prime square, but that is if a b are non-zero. So I am assuming this a prime and b prime not simultaneously 0, then that thing is I can write some cos theta. Okay, so just let me write that. So let me write this as cos theta into sine omega t plus phi, plus this is again like b prime by this thing, that is 1 minus cos theta, so this is again sine theta into cos omega t plus phi, where I will write for the cosine t, what is cosine t and sine t. So here cosine theta is just a prime by root over a prime square plus b prime square. Okay, and similarly sine theta is b prime by a prime square plus b prime square. Okay, so then I can write this as sine of omega t plus phi plus theta, right? This is just the sum formula of that. So that is equal to root over omega t plus phi plus theta, but the theta is just defined before. Okay, so this is a clearly, and this root over a prime square plus b prime square, this is a real number, and this total thing is belongs to also real number, so this total function belongs to w. So this is closed under this addition. Now let's go to this scalar multiplication. So there again you similarly have benefits for c f phi of t. This is by definition c times a sine. Okay, just let me write it here, that why this is belongs to. So this is nothing but f of root over a prime square plus b prime square comma phi plus theta, right, of t. So this is belongs to here. In this same case you have omega t plus phi, but that I can just simply write ac of, just combine a and c together, and sine omega t plus phi. So that is again f of ac comma phi of t. So this is also clearly belongs to w. So this shows that from 1 to that this w is a R subspace of this R power R, and w is a R subspace R power R. Fine. Once this is a subspace, we need to calculate the basis of this w. But any element, just if we see the representation of this f of a phi, so we can clearly get the basis. So for b, for any a comma phi belongs to R, f of a phi of t, what is it? It is a sine omega t plus phi. But that I can again like break by some formula of sine. So that is a sine omega t cos phi plus a cos omega t sine phi. Right? Now this a and phi are fixed, so I can just write it as like a cos phi times sine omega t like plus 0, so that this is a this sine omega t plus 0, this is a like here you have one as a constant and 0 is the angle here, and in this case a sine phi into cos omega t again, so I need to write in sine. So cos of omega t is same as sine omega t plus pi by 2, right? So this is sine omega t plus pi by 2, and that is again same as this a cosine phi, that is a constant. Let me write that as like some c1 and this is c2, then this is c1, this is f of 1 comma 0 t plus this is c2 f of again 1 comma pi by 2 of t. So this was an arbitrary element of the subspace W, and that I can write as a linear combination of these two functions, right? F of 1 0 and f of 1 comma pi by 2. So this implies that this W is the span of these two. That means these two generates the vector subspace W over R. So this is f of 1 0 and f of 1 pi by 2. Right? Span of this. But these two are also linearly independent. That is easy to check, that the sine omega t and cosine omega t, they are linearly independent, because if you take a linear combination of sine c1 sine omega t plus c2 cos omega t equal to 0, then this is true for all t. So in particular you take like t to be 0, then you get c2 is 0, and once c2 is 0, then you also get c1 times sine omega t is 0 for all t. So you can take like pi by 2 omega, so that will again give you c1 is 0. So these two functions are linearly independent, and this is span your whole W. So and just writing 1 0 f of 1 pi by 2 are linearly independent. So this is a basis, okay, and that means the dimension over this thing is 2, right? So this implies 1 0 f of 1 pi by 2 is a R basis, and dimension of W R, this is 2. Fine. So is there any question here?
No, sir.
Okay, thank you. So then let's go to the next one, the remaining two parts of this. So if you have a similar function, any function f in W, then you can actually you don't need to vary your a and phi over whole R, but it has uniquely, like each element of that thing is uniquely written as a sine omega t plus phi for any a positive, and phi is in between this 0 to 2 pi, 0 included, pi excluded. And second thing is you can define a like first of all linear map from W to C with the usual vector space. C is a vector space over R with the usual addition and scalar just scalar multiplication. And so then this is actually a vector space isomorphism, that linear map. Okay, so first one again, so this once you have f non-zero on this, so I know if f belongs to W, so f not equal to 0 belongs to W, implies that there exists a comma phi. I'm just writing that a and phi itself, or let me write as a prime phi prime belongs to R, such that ft equal to a prime sine omega t plus phi prime for all t belongs to R. Now I want to like find a which is positive. I don't know here a prime is positive or not, and a phi which is in between 0 and 2 pi. Okay, first of all note that once we have phi prime belongs to R, by division algorithm I can write that by division algorithm I can write phi prime equal to dividing by 2 pi, so it will be 2 pi into k, some like integer k plus phi, such that this is 0 less equal to pi less than 2 pi. This is just the standard like division algorithm of this. So and k belongs to z. I can always do that. Fine. And then this sign, this implies sine omega t plus phi prime. This is same as sine omega t plus 2k pi plus phi, and this 2k pi plus sine omega like omega t plus sine 2k pi plus 2 omega t plus phi, that is same as sine omega t plus phi, right? Because this sine has 2 pi period and k belongs to integer, so this is the same thing. Now if your a prime was negative, so now this ft I can write like a prime sine omega t plus phi, and to make this a prime is positive, so take this a prime sine omega t plus phi if a prime greater than 0. If it is less than, so f was non-zero, so I must have this a prime is non-zero, right? So belongs to R, so a prime is clearly a non-zero, otherwise f will become 0. And in this case you take minus a prime, then I had to adjust this minus with inside sign, so that I can do, because that I can write sine omega t plus pi plus phi, right? Because sine pi plus theta is minus sine theta, right? So that sign is a prime less than 0. And if this theta plus phi, like pi plus phi is again greater than 2 pi, then I can simply arrange that to get back to a phi which is in between 0 and 2 pi. Okay, so and so in this way we can manage this a is positive and phi is in between 0 to pi. So why this is unique? So suppose you have two representation. One say ft is same as some a sine omega t plus phi, and which is same as some a prime sine omega t plus phi prime, and both phi prime in between 0 to pi, a prime positive, like both are positive, and phi prime in between 0 to pi. If this is the case, how do you show that this a and a prime are same? First of all, I will show that this a and a prime are same. A and a prime are same. How do you show? So once you need to use that sine square theta plus cos square theta equal to 1. That's the only thing here. So I can write a equal to, as a is positive, or let me write a square equal to a square cos omega t plus phi square plus a square cos square omega t plus phi square, right? So this is a square sine omega t plus phi square plus a square cos omega t plus phi, this square. But this is same as a prime square sine omega t plus phi prime, this square, and this is cos square omega t plus phi, that thing is 7 root over of 1 minus sine square, and 1 minus sine square this thing. So ultimately we will get this is a prime square cos square omega t plus phi prime. Okay, but again you use sine square theta plus cos square theta equal to 1, so this gives you a prime square. Now this implies that a equal to plus minus a prime, but as a and a prime both are positive, so you have a equal to a prime. Once you have a equal to a prime and that is positive, so I have this also implies that cos omega sine omega t plus phi is same as sine omega t plus phi prime. But if this sine is 2 pi periodic, so if two values are same, then I must have this omega t plus phi minus omega t plus phi prime. This is some 2k pi for some k belongs to z. And this is belongs, that means you have phi minus phi prime equal to 2k pi, but phi and phi prime both are in between 0 and 2 pi, right? So their difference cannot be a multiple of 2 pi. This is only possible if k is 0, otherwise it is not possible, right? Because if you like subtract two angle phi and phi prime, so their difference cannot be like bigger than 2 pi unless so as so this implies actually this k equal to 0, this equal to phi prime, as 0 or 0 less equal to phi minus phi prime. So I am assuming this phi is greater than or greater equal to that thing, otherwise you have 0 to pi. So I am just taking this modulus phi minus phi prime, this is less than 2 pi, so I must have k equal to 0. So hence a and a prime same, phi and phi prime same, so this representation is unique. So the representation of, note that this, if f was 0, then I could have take a equal to 0 and phi is anything, so that whatever phi you take in between 0 to pi, each will work. That's why this uniqueness is appearing only for f not equal to 0. Similar thing you know in the complex number, that every non-zero complex number you can write it in the form of a e power I phi, right? Where a is the distance from the origin and phi is the angle that makes with the positive x-axis. So similar thing also happening in this representation. So that's why this actually like kind of map you expect from this W to C. Okay, so that we'll discuss next. So So D is we have this gamma from W to C. It takes a sine omega t plus phi. So for the simplicity, as we just seen that any f non-zero is has unique representation of this a and phi in terms of, so I can just take a is positive and phi is 0 to 2 pi, and gamma send this to a e power I phi. Okay. So this is that means it is the polar representation of the complex number. So it is very much well defined map. So onto it is clearly onto, because if it is 0, then I can simply take the 0 on the W, and if anything non-zero is there, then I know that I can write in the form of r e power I theta, where r you just take r sine omega t plus theta. So this map is clearly onto. And also, okay, so first of all we need this map to be a linear map to claim that this is a R vector space isomorphism. Okay, so first that gamma is linear. To show linearity, again I need to check that if I add these two things here, that will be added up here. Okay, so we have just seen in the previous part that when we add two things here, that will give us this kind of thing, right? Sine omega t plus phi plus theta. So I'll just borrow this thing here, that a sine omega t plus phi, if I add, and with b sine omega t plus psi, that gives me some a prime and b prime. So root over of a prime square plus b prime square into sine omega t plus phi plus theta, where cos theta was this cos theta was a prime by root over of that thing, and that is actually a plus, if I just go back, so this a prime was a plus b cos psi minus phi, and this is b sine psi minus phi. Okay, so this is a plus b cos psi minus phi by root over of this a prime square b prime square. So this is my was a prime, and this is just simply a prime square plus b prime square, and sine theta was just b sine. So this is b sine psi minus phi b prime square. Okay, now in this case, this a prime square and b prime square, this if I just square add and see, then this will give me a square plus 2ab cos psi minus phi plus b square, because b square cos square theta psi minus phi plus b square sine, so that gives me b square. Okay, so let me write that. So root over of a prime square plus b prime square, so this is actually nothing but a square plus 2ab cos psi minus phi plus b square. Okay, and this thing this a square you just write as cos square phi plus sine square phi. This b square you write this is just a just to manage thing, to see this is a linear. So I need to show that this I know gets mapped to root over of a prime square plus b prime square into e power I phi plus theta, right? But that I need to show that this is same as a e power I phi plus b e power I psi, right? So to manage that thing, I'm just calculating this one. Okay, so this one is actually nothing but that I can write a okay, just let me write in this form that a e power, if you take just e power I phi, right? Yes, e power I phi modulus of this square, so that means a square cos square phi plus sin a square sin square phi. This is a, and okay, this is actually modulus of a plus b e power I psi. Just check that this is just that thing, the same thing. So cos phi cos psi plus sin phi sin psi, that will give you this thing. So this thing is this, and this if you just expand the sin omega t plus phi plus theta, so or e power I theta plus phi, so that is e power I theta into e power I phi, e power I phi. But e power I theta is cos theta plus I sin theta, right? I sin theta. So cos theta I know, just if I put here that this is a plus b cos psi minus phi plus I b sin psi minus phi by root over of a square plus mod a square plus b square, which just writing same a prime square plus b prime square. Okay, and if you just combining this one, then it is saying that it is a plus b e power I psi minus phi. This is just cos psi minus phi plus I sin psi minus phi, be it common, so this is that b prime square. So this is, now I get that this is e power I, like phi I first wrote, and then this is a plus b e power I psi minus phi by root over a prime square plus b prime square, right? So this is root over a prime square plus b prime square into a e power I phi plus b e power I psi. So that's what we wanted to get, and this is nothing but just the modulus of this thing. So finally, if I just write this gamma map, this is a sin omega t plus phi plus a sin, b sin omega t plus psi. This is in one hand gets mapped to by this thing, that gamma as it defined. So one hand it gets mapped to a prime square b prime square into e power I theta plus phi, root over of a prime square plus b prime square into e power I phi plus theta, but we just have seen that e power I theta plus phi, this is same as this thing, so this is nothing but a e power I phi plus b e power I psi, right? So that's what we wanted to show. So this is nothing but gamma of a sin omega t plus phi plus gamma b sin omega t plus psi. Okay, so this actually we don't need this one. Yeah, we don't need this one. So we just use the definition of theta here and see that this thing is that we get this one. So gamma, this shows that gamma is additive, but still we need to show that this is scalar multiplicative also. Like if I take, but that is easy because if I take gamma of c times a sine omega t plus phi, that is ca of sine omega t plus phi, so that is same as ca e power I phi, because here the a is transferred to ca, but that is same as c times a e power I phi, and that is same as gamma of a sine omega t plus phi. So hence gamma is linear, hence gamma is a linear map from W to C. Now the easier thing, like this is linear map, and also on to 1 1 also one can show that 1 1, if it is to show this is 1 1, we need to check that the kernel of this map is 0. But what is the kernel? So all those elements which gets mapped to 0. But if anything a e power I phi equal to 0, that means e power I phi is, cannot be 0, that never 0, so a must be 0. Once a is 0, that means a sine omega t, this total element is 0, so the kernel is of this gamma is 0, so that means it is injective and also surjective, hence it is isomorphism. Also, as any complex number has polar representation, so gamma is on to, also like kernel of gamma is 0, hence gamma is bijective. So bijective linear map, this implies that gamma is isomorphism. Isomorphism. Fine. The next part is okay. This is the next part we just have done. Okay. So any question here?
No, sir.
Okay, fine. So then let's go to another problem. So here this thing said that if you have a vector space, k vector space with dimension at least 2, then, and also if you have a additive map, just additive map, not like scalar multiplicative of that thing, no, it is not saying, but saying this is just additive, that means f of v1 plus v2 is a v1 plus a v2, and it also satisfies that if you take any x belongs to v, then the subspace generated by x, that means that we denoted by kx, f get like maps kx to inside kx. Okay, so so that, what does that mean? So for any x belongs to v, f of kx, so this is a total subspace of the vector space v, this is contained in the subspace kx. That means what is the general element of this this subspace? Some k times some scalar times x, right? But in particular k is field, so I can take just x. So this implies actually f of x, that is some scalar times x, because it is lies in the subspace kx. So it is some, I'll write ax times x, where ax for this ax belongs to the field k. Okay, so now what need to show that this actually this map f with these two conditions, that this is additive and this thing, then this is nothing but a just a multiplication map, that is called homothecy. for some fixed a belongs to the field k. So let's fix some x, fix x. Then I know that this x is x times x, just using this thing. Now take any y belongs to v minus kx. That means y is not of the form some c times x. Okay, that is y not equal to cx for any c belongs to the field k. Okay, then I will show that this then for this y also I know that this fy, this still have the form some ay constant times y, because ky is again contained in ky. So so this thing for some ay belongs to k. But if I can show that this ay is equal to ax, then I can say that this ay and ax is same for all y belongs to, for any I fixed x and varying y, so ay is still ax. So take that all that ax equal to ay equal to a, and that will solve my requirement. So how do you show that? Then I need to use this additiveness of this map. Still we haven't used the additiveness. So what I can use, so I know that due to the additivity, f of x plus y is fx plus fy, right? And fx is, I know, x times x, and fy is y times y. But this is also a element in the vector space V. So this also f of x plus y is some a x plus y of x plus y, right? Now if you just take all the things in two sides, so then it give me that a x plus y minus ay. So ax plus y ay, just as I'm writing that as a subscript to note that this is the corresponding scalar for this vector x. Okay, so this thing into y is ax minus ax plus y of x. So this shows that this x and y are linearly dependent, right? Unless this ax plus y minus ay is non-zero. If this is non-zero, then I can simply take its inverse and say that y equal to some c times x, right? This inverse times this one, which is belongs to k, because in k non-zero elements are invertible. So by this thing, by star, this is only possible if this and this both are 0, right? Then only I can have because x was fixed. Okay, let me fix x non-zero, that I need to fix. Otherwise if x is 0, then it is 0 anyway. So, and y is clearly v minus kx, so 0 is not there, y is also non-zero. So I must have this is ax plus y. So this condition actually is saying that this y and x are linearly independent, but this case you are getting linearly a linear condition of that thing. So that means that ax minus ay equal to 0 equal to x minus ax plus y. So that means that ax equal to ay equal to a x plus y. So that's what we wanted to show, that for any x and y I have ax equal to ay. I fixed x and varies y over remaining thing. So hence this is true for all the element of v, that f of v equal to ax v, because ax is anyway not changing, so that x you define to be a. So hence f of v equal to, so take that to be a, and this is ab. for all elements to be. So any vector that is additive and satisfying this condition in particular is linear. So this is also a part of this theorem. Okay, so still, okay, let me just briefly say next problem, that if you have a two homomorphism of k vector space f1 and f2, v2 v1 and v2 v2, okay, then the k linear map f is defined v to v1 cross v2 is just pointwise. You take f1x, f2x. This is isomorphism if and only if f1 is surjective and the restriction of f2 to the kernel is bijective. So it is again like isomorphism, that means it is injective and surjective. So linearity again follows if is like f1 f2 both of the component are linear, so f is also linear, so that is not a problem. And f1, now suppose this is isomorphism, so if this is isomorphism means this is surjective. So if I pick any element from v1 cross v2 that has a pre-image, so in particular that means that f1 and f2 both are surjective, right? So it is just f1 is surjective. So and with this condition saying that if you restrict your f2 to the kernel of f1, that is bijective onto v2, because okay, so bijective, so to show this is bijective I need to show that this is injective and surjective. So injective, for injectivity I need to show that kernel of this f2 restricted to kernel f1 is 0. But if anything like, okay, so just let me show that thing, that kernel of f2 restricted to kernel f1, this thing is nothing but just kernel of f2 intersection with kernel of f1, that's it. But if this is an isomorphism, so that means that kernel of f is 0, but kernel of f is 0 means the kernel of f1 intersection, because kernel of f consists of all those x where f1x is 0 and f2x is also 0, that means that belongs to kernel of f1 intersection kernel of f2, right? So this is 0 if f is injective, and conversely if and only this is injective, then this is, and also this is how this is restricted to, this is on to like surjectivity for any v2 belongs to like v belongs to v2, then you can simply take 0 comma v2. So 0 comma v2 belongs to v1 cross v2 and this is surjective, so that means that has a pre-image say x, such that f1x equal to 0 and f2x equal to v2. So f1x is equal to 0 means that belongs to kernel of f1, so x belongs to kernel of f1 such that f2 of x equal to v. So this is again bijective. So hence this is proved, and conversely also true that if this is so this is the injectivity just implies the injectivity of this, and this bijective also implies that f2 and f1 is surjective, so that thing gives the bijectivity. Okay, so that's how you prove this one. And some other problem is also I thought about so this is actually from the previous assignment. This I will just give a hint and write in the PDF, I'll upload it, and this algebra thing I may do it next time. Okay, just so to have the feel of the in the like this current assignment 6 you have some problem related to this algebra thing, so this I will write at least this one, and write the PDF, so you can find that thing, this thing, and more about the algebra map and algebra thing, that will probably discuss in the next tutorial or something related to that. Okay, so are there any question? Otherwise we'll stop here and we'll meet next week then.
No, sir, there is no question for now.
Okay, Okay, so okay then bye, and we'll meet next week.